Hello and welcome to another episode of Double Electronics. Today I'm going to be talking about repairing a light stand which is broken. This is a pretty special light stand, is that when you hit the base with your hand, the light will turn on to 3 different levels depending on how much times you hit it. So the problem is that this light stand only stays on when you plug it in. You can't change the levels with touch sensitive base, or actually capacitive base. So this uses a regular incandescent light bulb. It's a standard filament in there, nothing special, just a 2 on and off such type of lamp. The base is a regular light socket. There's no 3-way socket in there because we're missing a copper section right there to make it a 3-way lamp. So it's just a regular 2-way lamp. So they must be doing a thing with the Triac in there to lower the voltage on the light to get the different levels. So under here is just a regular plastic base. Kind of already taken this apart just to get a first look at that. And this base is just heat sealed in to the metal base. And what we have right here is that we have the mains coming in here. The hot wire goes into the box, red wire goes out and then into the lamp, and then the white wire, which is a neutral, goes into the base, and that also goes to the lamp too. So what we're controlling is the hot. So there's a switch inside here which can turn on and off the hot wire. The green wire actually goes to the base and not actually to ground. So that's kind of interesting because there actually is no ground on here. So this could actually become electrically active if one of these wires were to short into the case, like the hot wire. So that's a little bit of a safety risk. But apparently it's still got a UL listing, so I don't know. So what's inside this black box is that it's a touch lighting control, it says on the cover. The MT1001, got the schematic on there. Green wire goes to the touch plate. Red wire goes to one side of the lamp. Black wire goes into the black box and then to the plug. White wire goes to the plug and also to the lamp. So, on the back of this black box, it says touch lighting control. It says incandescent only on it, so that's kind of interesting. I think any fluorescent light was not going to be able to dim that great with it. And then there's the UL listing number. There, it's E301787. So I plan to reverse engineer this box and figure out how it works, and then see if there's a broken part in there that's keeping the touch sensitivity from being fully utilized. So here's a close-up of the board. Looks like you've got a Triac right here. A few passives are on the outside, and then a blob microcontroller on a separate board. So I'm going to reverse engineer this now. Start. So this Triac, I'm guessing, is a BT136-600E. So I'll go over here to the web browser and look at it. BT136-600E. Okay, so here's a data sheet for it. It's just a regular Triac. So yeah, I can do bidirectional switching, so that's what we need for AC. The voltages great for 120 volts. Can handle that. 4 amps. Yep. So okay, there's some important stuff right here is the pinning on the chip. So you know which pins go where for the Rice.Engineer. And just got a bunch of graphs how the silicon works. Dimensions. Alright, so the pins are, so pin 1 it goes from left to right. So pin 1 is main terminal 1, which is, what is it? Pin 3 is gate. Main terminal 2. Let's go to from data sheet. This one's kind of, okay, looks like a more updated one. Here we go. Main terminal 1 is T1, and main terminal 2 is T2. So pin 1 is T1, which is right here, and pin 2 is T2, which is right there. And then the gate is pin 3. Okay, so you can draw that. I think I'm just going to start with the Triac. Okay, now I got the Triac through. I've switched to webcam now since my main video camera is out of batteries. So there's a Triac. This is it's going to control the AC. So I'm not going to be surprised if that goes right to the input and output. This is right up here that the red is going to the lamp. The black is from the AC hot. And what else is there? Green coming from the case, and the white going to neutral. Okay, so let's see where T1 goes. This is a pretty easy circuit board, so it's really easy to follow. There's nothing underneath the Triac. So 1 goes to the microcontroller, 1 pin on the microcontroller, I guess, and then 2 T1 is pin 1, yep. That goes to black. So T1 goes to the black, which is AC hot. And also that hot goes to other things too on the circuit board, but we're just going to cover the Triac for now. And red, pin 2 goes to the red, which is the lamp. So that goes to lamp. And then the lamp goes neutral. I got the completed schematic right here. As you can see, the lamp is down here, and the controller is right here. And the green wire goes into these two capacitors, which can detect the capacitance of the human body. So it goes through these kind of circuits right here, which will detect the human body or not. So to vary the lamp brightness. And then the pin 8 is the output to the Triac, which controls the lamp. And I did a bit of searching online for this integrated circuit, and I found a pretty good one that matched the pinout of it. Like 8 is output, pin 6 is unconnected, 7 goes to one of the rails of the AC, and there's everything matched on it, so I think it's the same IC. It's the TT6061A or TT8486A IC. So as you can see, the circuit diagram is very similar. You can see there's capacitors separating the touch plate from the controller, and there is the BT136 Triac in the circuit. So that's the same Triac which is on the circuit board that I reverse engineered. And these pins match the pins I reverse engineered. So it's a pretty good match for the system. And you can see there's a Zener diode there. There's these diodes right here. So like everything matches. So I'm going to rewrite the circuit that I just drew into this form to make sure that it's very readable. This Zener diode forms a voltage regulator. So the mains will come in, it's rectified right here. It goes through a resistor, and then it goes, then the Zener diode makes it into, it regulates the voltage on the AC, and then this capacitor smooths out that AC into DC. This one actually. This one smooths it out so it's a steady voltage, and then that's what the IC runs on. Looks like 6.8 volts. And the 7 is the reference. And what was interesting is that this wire right here is actually the hot wire, and then this is neutral. So it's reversed from what I thought it would be. So that's interesting anyways. So I'm going to just redraw this. Like I took a picture of the original circuit, so I'm just going to erase everything and then start over. Draw a new one. When a person touches something, 60 hertz frequency is introduced into the circuit, just based on the capacitance of the person and everything else. It'd be 50 hertz in a country with 50 hertz. So this would go in. It's really low power. Like it's really it's in millivolts. So it's not a lot of power going at all. Very small amount. It would go through these two capacitors. It would AC couple through them, and it would go through that resistor. These diodes right here actually clamp this voltage, so it doesn't go above or below the voltage that the chip is using. So it's not going to go above the rail, which is the VDD of the chip, which is 6.8 volts set by the Zener diode, or it won't go below the ground, you can call it. It's not really ground, but it's the chip uses this as a VSS, so it won't go below what the chip is using for power, just so it doesn't damage the chip in case something a higher end frequency would be in contact with the touch plate. And you go through this 1K resistor just for current limiting or something, and you go into this touch input. So here's a block diagram of the inside of the chip. So the induced frequency into the circuit would go into the touch detector black box, and it would get summed up with a CI input, which is the CI input is a sensor control input. So that goes to the VDD. Through 8.1 ohm resistor and capacitor. I'm not really sure what this part of the circuit does, since there is no sensor on this. Okay, so their inputs are clock and frequency input. And the clock line comes from the AC input over here, goes through a resistor, and then goes through a diode to halfway rectify the signal. So the clock input would look like this. So that's a pretty stable clock. You could use that for a clock. That's what many clocks use. Old school clocks without a crystal. Line frequency operated clocks are kind of cool. But that's the same concept. It goes right in there and then uses that for a clock. The frequency input takes the frequency directly from the mains input through 1 megohm resistor, and that would just be, you know, like going, it looks like that, and it'd probably do some signal processing, signal conditioning to get it into a usable format. So it goes, the clock input goes in the frequency generator, the frequency input goes into the zero crossing detector. So this will detect when the circuit crosses, or when the input voltage crosses a zero line. That's important for your firing the thyristor, the Triac. So these both go, these all of them go into a counter and decoder. The touch detector goes to a step register. So the step register, I think, stores the information for the lamp brightness. So the first one would be the lowest amount, the second one would be the second highest, and then the third one, the brightest. I think it'd just be full on, and then the last one would be shutting off the lamp again. So maybe that's what the step register does, and that goes in the counter decoder, which takes everything and then sends it out to the AT, which is the angle trigger output, and that goes to the Triac. So there's AT output, and AC couples through a capacitor, and then through a resistor, and then goes to the gate of the Triac, which is right here. And this pulse would be, this would just be a pulse following with the AC line. So say you've got AC signal. Right here, just say that's 60 Hertz. So what this gate signal would be is that if the lamp wanted, if you wanted to turn on the lamp for like 50% of the time, you'd apply a pulse right here, and then this would turn on the lamp. The lamp would be off right here in this section, and then it would turn on with a gate pulse and then stay on until it crosses zero, and then it would stay off. And then if another pulse happened right in the middle of the signal, it would turn on to the negative part and then go to 0 again, and go off, and then it just repeats over until you get 50% duty cycle. So what we have right here is a RC snubber, which goes across the Triac terminals. This is usually used for inductive loads, but this bulb is mostly in a resistive load, so it's just an extra thing they use to protect the Triac in case there's some sort of line surge or something. Since voltage can't change across the capacitor instantly, it will limit the amount of change in voltage over change in time that will occur across this Triac. So if you have like a sharp impulse of voltage, you can say, across points A1 and A2, if a snubber circuit was installed, it'll be a much, I'm kind of exaggerating right now, but it'll be a much more gradual change in voltage because the capacitor has to charge, versus if it wasn't there, it'd be a sharp pulse which could damage the Triac, or it could turn it on. So it's just a pretty good design to put one in. And they also included this, which wasn't included in the example schematic, which I found online, just to limit the current going into the Triac. Another thing is that in this schematic, the 1K resistor goes after the diodes, and on the schematic which I found, it actually goes before the diodes. So I don't know, it's just certain little things are switched around. You can see there's no resistor right there, and there's no snubber circuit in this example circuit which someone has made. This is actually for 230 volts AC at 50 Hertz. So a few of the components are different values, like they're using 3 capacitors instead of just 2. And they're lower capacitance each. I think this is probably provide a higher blocking voltage because it's a higher mains voltage. So first we're going to check between A1 and A2 to see if there's a short in the circuit. So I'm going to check the Triac for resistance between the terminal A1 and A2. So A1 corresponds with pin 1 and A2 corresponds with pin 2. So I'm just going to go between these two terminals right here and read the ohmmed. So we're reading about 0.3 ohms with the positive lead on the A1, and I'll check it the other way. We're getting about 0.3 ohms the other way too. So it looks like there's a short between A1 and A2, so that's a pretty good sign. I'm just going to try shorting out the leads to make sure the gate isn't charged with any residual charge. I'm going to try it again. And we're at 0.3 ohms, and it's probably 0.3 ohms the other way now. Yeah, 0.3 ohms. This is probably even the lead resistance is 0.3 ohms. Let's check. Yeah, so we're at a dead short between pins A1 and A2. So that could explain why the lamp is staying on, no matter what the control circuit is trying to do. So it looks like I don't have another Triac in my stock, so I'll have to get a replacement for the BT136, which I'll be posting another video or replace the Triac and see if the lamp works after that. I'll be posting a complete schematic on my website, which I'll convert this into an actual schematic on the computer, a PDF, and be putting online just for general use and reference. And this is for the MT1001 touch lighting control circuit. All right, that's all for this video. Hope to see you in part 2, which I'll post a few weeks from now.